Good morning to all. This is Maulika, Assistant Professor, Department of Physics from St.Josephs College of Arts and Science for Women, Hosur. In this video, I am going to derive the derivation of Poiseuille's formula. Before derive the Poiseuille's formula, we should know that what is viscosity. Viscosity is defined as the resistance to flow. At a molecular level, viscosity is a result of interaction between the different molecules in a fluid. This can be also understood as friction between the molecules in the fluid. Water, ethanol, methanol, diesel fuel, and kerosene. These are examples of low viscosity. And ghee, peanut butter, dish soap, these have high viscosity property. And the fluid has two types of flow. One is laminar flow or streamline flow, the another one is turbulent flow. Streamline flow is in a fluid's smooth flow with the velocity less than the critical velocity. The turbulent flow is in uneven, unstable, and exceeds the fluid's critical velocity. Laminar flow is quite slow mover water characterized by water particles moving in a straight line within the parallel layers. The turbulent flow, on the other hand, is louder, fast moving water characterized by erratically moving with water particles that mixed between the parallel layers. Is the flow of water in a pipe, and an example of turbulent flow is the flow of water in the river. The water flows chaotically around obstacles in the flow. This Faisal's formula is used to find the flow of liquid through a capillary tube, and it is only suitable for streamline flow. This image represents the cross section of the capillary tube. Suppose a constant pressure difference is maintained between the two ends of the capillary tube. The length of the tube is L and the radius of the tube is A. Consider a steady flow of a liquid of coefficient of viscosity is eta through the tube. The velocity of the liquid is a maximum along the axis and is zero at the walls of the tube. Assume that there is no radical flow. Consider a cylindrical shell of the liquid coaxial with the rubber tube of inner radius r and outer radius r plus dr. Let the velocity of the liquid on the inner surface of the shell v and that on the outer surface is v minus dv. The dv by dr is the velocity gradient. The surface of the shell A is equal to 2 pi RL. According to the Newton's law of viscous flow, the backward dragging tangential force exerted by the outer layer on the inner layer opposite to the direction of motion. So the force value is minus eta 2 pi RL dV by dr. Here the flow is opposite to the direction of motion. So minus sign I am putting here, and the driving force on the liquid shell accelerated it forward. The value is P pi r square, where P is the pressure difference across the two ends of the tube and pi r square is area of the cross section of the inner cylinder. When the motion is steady, we know that the backward dragging force is equal to the driving force. Next, I comparing the dragging force and driving force. From this, I got an expression dV is equal to minus P by 2 eta L or dr. Next, I integrate dV over the limits 0 to a. After integration, we can obtain the average velocity of the liquid flowing through the cylindrical shell. Hence, the volume of the liquid that flows out per second through the shell is area of the cross section of the cell of radius and thickness into velocity of flow, and that value I am going to integrate the limits 0 to a. So finally we get pi p a power 4 upon 8 eta L. This expression represents the flow of liquid through a capillary tube. Then Poiseuille added two corrections to this formula. First correction for pressure head and the second correction for length of the tube. By adding these two corrections, we can get exact formula for the flow of liquid through a capillary tube. Thank you.